bridge demolition schemes, basement propping schemes, facade retentions, etc. Today I'm going to run through a case study on the Majestic facade retention in Leeds. We provided the design for the scheme from concept stage and produced the detailed design drawings, fabrication drawings, and the connection design on the scheme. We'll go through the questions at the end with rates. So before I go into my presentation, who are we? Who are Andon? We've been around since 1990 and now operate from 3 offices across the country in Chelmsford, Newcastle under Lyme and Aberdeen. We specialise in temporary works design, demolition engineering and lifting gear design. As a part of this, we're getting involved with a lot of bridge demolition schemes and rail schemes. And as you can see from these photos on the screen, it's really interesting work and it's rewarding to see it when the demolition schemes come up. So onto the Majestic. The existing structure is located in Leeds city centre. So it's very close to Leeds station, which is one of the busiest stations in the north of England, which is located just over here, if you can see the pointer. The structure is a really well-known structure. It was constructed to be a cinema in 1922 and has since been used as a bingo hall, ballroom, and then became a nightclub in the 1990s. In 2014, it was ravaged by a fire, which left it in this derelict state. Temporary scaffolding was put up along this space and along this space to support the top portion of the wall, which you can see here and here in the aerial shots. This was to allow the roof trusses to be removed following the damage caused from the fire and the increase in wind loads that the walls would now receive, with them now being sort of a parapet of freestanding wall. So the proposed structure. The proposed works included the full demolition of the existing internal structure down to basement level. The grade 2 listed 14-metre high facade was to be retained as a part of the works, and following the demolition, a new structure was to be installed, a new steel structure with a central reinforced concrete core transforming what was an empty shell into a usable office space, whilst maintaining its heritage value. Andon were employed by Armac Demolition, who undertook all the demolition works on the scheme. Armac were employed by Sir McAlpine, who were the main contractor on the scheme. The terminal works design was by Bureau Happold. So the main item of temporary works that we undertook on the project were the facade retention, which I will be discussing in this presentation, the basement propping, which was required to remove the propping, to replace the propping action of the existing ground floor slab. We also undertook other items of work such as propping design, plant justifications, demolition sequencing, and we'll now basically anything to aid, any temporary works designed to aid the demolition. I'll now go through the facade retention. So the brief was to provide a fabricated facade retention design that would enable the full demolition of the internal structure down to basement level, whilst being as unobtrusive to the demolition and construction works. Typically, there are 3 main types of facade retention system. So utilising the existing structure that remains, so propping back to other cores or shear walls that remain in the structure. This wasn't possible in this due to the sheer quantity of demolition. Utilising frames at regular centres to restrain the wall. This would have caused access issues, but was a plausible solution. And using trusses or wailers that span to towers to restrain the walls. To determine which route to take, we needed to establish where the structure needed support. When we'd established this by looking at wind loadings, etc., and the capacity of the wall, we needed to look at how we could provide the support in the most efficient way. We started out by overlaying all the AutoCAD files of the existing and the proposed structures within the 3D model of the facade that you can see at the bottom of my screen here. This defined effectively what the challenges were with our design. So one of the key things on this side was access was to be maximised. The scaffolding, which I showed you on the aerial view, that was located along this space here, along this space here. So that scaffolding was supporting a portion of the facade, so it couldn't really be removed until our new system was in place. So our system had to be designed to fit around it, which obviously influenced our design. Avoiding the existing and proposed structure, I think that's a fairly obvious one. The site constraints, which are the key one, was on Quebec Street, which is here. The footpath narrowed, creating a bit of a pinch point in this location, which affected our design. The services in the existing footpath. So there was a large Openreach chamber, which was located around here, that affected our design, because we had to account for it. And fixings to the wall, we wanted to make sure that we didn't damage the facade. It was a good looking building, so we looked at detailing a clamping solution. The next stage was how this support could be provided. And given the limitations, using trusses and towers seemed the obvious choice. So this led us to this concept. So to position the towers, we had to account for the existing scaffolds, as I mentioned, which led that and the fact that the Quebec Street came close to the structure led to there being an internal tower. The existing scaffolding on Wellington Street, which is there, led there to be a much larger span between two of the towers than the other ones, and it also meant that this tower here was located over the existing chamber, which was not ideal, but was the preferred option by the site team rather than having an additional tower on the inside of the structure. So how do these towers work? This section here shows a simplified load diagram for our concept, where the load is transferred down the towers, which act as trusses, where one leg is, or the outer legs are sort of tension cords. Stiff beams are also provided at ground level to increase lever on the base to reduce the Kentledge requirements. Pavement level, the Kentledge doubled as a large pad foundation to reduce the pressures to the pavement. At the basement level, an internal leg would also require a small portion of Kentledge to resist overturn. This concept was sent to the client as a 3D model, which you see at the bottom here, for them to insert into their model and comment on at an early stage. We also had meetings with all the parties on site to discuss the project before we commenced our detailed design. This was beneficial because we could explain why we had got to the solution, how it worked, and make sure that everyone was on the same page. It also allowed for a more collaborative approach. It was agreed, for example, that the new basement wall construction will be brought forward, which enabled us to tie into this to resist uplift rather than relying on the Kentledge within the basement, which is obviously a benefit to the project. So following these meetings and the initial concept, we detailed the design fully along the lines of what we'd agreed. The plan that you can see here shows a section from an extract from our GA drawing. I've increased the dimensions so that you can read them, because I think it's worth reading them to get a sense of scale. I mean, the largest truss was over 15 meters, which is quite a span. So the wall is restrained by the clamping action of the trusses and the internal whaler. The load is then transferred from the trusses to the towers, and the trusses are supported by gallows brackets and scaffold tubes at regular centres. And the scaffold tubes also act as a nominal restraint to the parti-cord of the trusses. The towers themselves were designed and detailed as pods to enable to make them reusable and to enable easy installation on site. And you can see from the photo at the bottom how the installation worked. It worked well. The scheme was drawn using technical structures, meaning that when we completed our design, we were able to issue the file to the fabricators to help speed up their sort of fabrication process. Obviously, our design output is our drawings, and that was what should be fabricated to. It just helped to speed up the process, because we found that fabricators quite often take our drawings and create their own model of the drawings to get all the NC data to color the plates. So effectively, we're trying to prevent repeat work. So I think there's a benefit to the project and the fact that we provide that information in advance. So the front wall of the structure, was arched in shape, which is sort of an inherently stable shape. To ensure that it remained in compression, we detailed tension cables that ran along the wall, ran along the front of the wall, and were restrained back to the towers. You can see the cable shown on our scheme drawings in red, and you can see the images, or the image of the cable laid along the truss and how it sort of goes around the wall to the packing. So here we can see some of the wall connection details. On the top left, you can see a section from our 3D model, which shows how we clamped around the wall with truss and had a internal weather as well. This model was used to create our scheme drawings, which there's an extract of that, this element of it here. And these drawings were then used to create the actual final thing on site. These were used to fabricate from, so that we can see the detail on site. It's just nice to see the full cycle of our inputs to the outputs, if that makes sense. You can see there's quite a lot of packing on the wall, which you can see here. This was due to a feature at the top of the wall that stood out slightly, so it meant that we basically had to be a bit of an offset to our truss. We detailed a strap that was attached to all of the timber, so that should it become loose, it couldn't fall. It would just be held by or caught by the strap. So the trusses were designed and detailed with standard connections throughout, and there's a standard infill piece that matches all of the towers, which you can see here. So the idea was that we would maximize the potential for reuse of the system by having standardized details throughout and standardized truss components effectively, meaning that when I suppose it would be reused, the only real adaptations would be to the lengths of the trusses to suit the neck structure along the line, I suppose. So the internal tower that I mentioned earlier was different to the other towers. It was constructed 3 pods as it was supported from basement level rather than the street level. This meant that it had slightly larger members, it had to be stiffer to account for deflections, etc. There was a larger internal whaler here as well, which you can see here and then here. So this whaler was tied using doodags through to the outer truss, and that was how we transferred the loading back to the tower. So on the left you can see we've overlaid a section of the proposed structure in our model to minimise clashes, and from the early meetings that we had with the client and their client, these clashes were expected, and we provided a 3D model to our client so that they could overlay it in the final in their model, which enabled them to plan around these clashes. On the right, you can see how it was installed on site. So the actual frame was tied down to tiles, which I think initially was going to be permanent works tiles, but due to the basement design change, so there was tiles installed specifically for this. One item that I mentioned before was the Openreach chamber that was beneath Tower 2. So basically, unless we went on the inside of the structure, which had been ruled out by the client, we had to be over it because of the position of the scaffold. We couldn't go further because the truss would have to span further. So basically, it had to be on top of it. Following discussions with Openreach, who own the chamber, we assessed the loading to the chamber. And as there was little information available, we used a sort of live load comparison approach to and concluded that propping was required due to the increase in surcharge loading. We had to make the tower's base larger as well to decrease the pressure further. And we also had to include an opening in the base to ensure that access wasn't restricted, which meant that strengthening the base was required compared to the other bases. We used an existing beam that had come from the demolition works to do this, reducing additional materials, I suppose, in the use in their design. The propping within the chamber was obviously not ideal given it was a confined space. Our preferred option was to fill the chamber with pea shingle, but due to the access requirements, this wasn't a viable option. We detailed a proprietary system that was as manhandleable as possible to reduce risks as much as we could. The loading directly above the chamber was also lowered in our design by the use of fill core, which compresses in a predictable way. So this basically meant that the base was fairly complicated to analyse, but we went through the analysis and proved that the loadings were, or the stresses within the chamber were no higher than the existing case. So the project, here I've attached a few images that show progress on the project as a whole. So when we came to site, the structure looked something like this. During the demolition works and the sort of first stages of construction works, the facade retention system is in place here. And then now, I think this photo was around a month ago, I got it from the Majestic Twitter feed. You can see the progress on the construction is coming on well, and it's getting close to its finished article. So it's been a good project, and it's going to be a good looking building. So that's it for my presentation. I hope you found the case study interesting. We'll now be going back through to an Angus to go through questions.